Imagine you are standing at 0 on a long straight road. The absolute value of a number is simply how far that number is from you, ignoring whether it lies to your left or your right. Distance can never be negative, you cannot be -3 steps away from something. So the absolute value is always 0 or positive. We write it with two vertical bars. The absolute value of x is written as x. It asks one question: how many steps from 0? In real life, we often care about the size of something, not its sign. If a bank balance goes from +5 to -5, the change is 10, the direction does not matter for the size of the swing. Absolute value gives us that size. It also tells us how far apart any two numbers are. The distance between A and B is a b. Engineers use it to measure error, how far a real measurement is from the target, regardless of whether it is too high or too low. In calculus, it helps us talk about how close two values are, which is the heart of limits. The rule is beautifully simple. If a number is already 0 or positive, its distance from 0 is just itself, so 5 is 5. If a number is negative, it sits to the left of 0. To find its distance, we flip its sign to make it positive, so -5 is also 5. 0 is exactly at the start, so its distance is 0. You can think of the absolute value bars as a machine that removes any minus sign. Mathematically, we say x equals x if x is greater than or equal to 0, and equals x if x is less than 0. That x does not mean a negative number, it means the opposite of x, which turns a negative into a positive. Suppose a weather station reports the temperature dropped from 4 degrees Celsius to -3 degrees. What was the total drop? The change is final minus initial, -3 minus 4, which is -7. But a drop of 7 degrees is a size, not a direction, so we take the absolute value. -7 equals 7. The temperature fell by 7 degrees. This same idea applies whenever you need the size of a change. In a factory, a bolt must be 10 mm wide, with a tolerance of 0.5 mm. An acceptable bolt satisfies actual width 10, at most 0.5. Absolute value turns a two-sided range into one clean statement. We already know absolute value means distance from 0, so it's never negative. But how do you actually calculate it for any number? The piecewise definition is a simple set of instructions. It tells you exactly what to do, but the instruction depends on what kind of number you start with. If the number is already positive or 0, you do nothing, just keep it. If the number is negative, you flip its sign to make it positive. That's why we split the rule into two cases at 0. Think of it like a sorting machine at a recycling plant. The sensor checks each item. If it's the right type, it passes straight through. If it's the wrong type, a mechanical arm flips it over so it's correct. The piecewise definition is that sensor and flipper for numbers. Knowing absolute value is distance from 0 is the idea, but to use it in math, we need a calculation rule. The piecewise definition is that rule. It's the bridge from the concept to actually solving problems. Without it, how would a computer or a student handle something like x, 3? They'd be stuck. This definition matters because it's unambiguous and works for every single real number you can throw at it. It's the precise, step-by-step recipe that makes the idea of absolute value useful in equations, graphs, and later in calculus. It's the difference between knowing a car exists and having the key to start its engine. Let's build the rule from scratch. Imagine the number line. For any number on the right side of 0, like 2 or 3.5, its distance from 0 is just the number itself. So for x greater than or equal to 0, the absolute value is simply x. Now, look at the left side. A number like -4 is for units from 0. How do we get positive from -4? We multiply by -1, which we write as a minus sign in front. So for x less than 0, the absolute value is x. Notice that x here is not a negative number, it's the opposite of a negative, which is positive. If we plot this, for positive x, the graph is the line y equals x, going up at a 45-degree angle. For negative x, the graph is the line y equals x, which also goes up to the left. The two lines meet at 0, forming a perfect V shape. Let's use our new rule on a concrete problem. Suppose a submarine dives to a depth of -7 meters, where negative means below sea level. We want to know its absolute distance from the surface, ignoring direction. Our input is x equals -7. The first thing we do is check the condition, is -7 greater than or equal to 0? No, it's less than 0. So we must use the second case. The rule for a negative number is to take the negative of it. That means we write -7 equals minus, and then in parentheses, -7. A negative times a negative is a positive, so -7 is +7. The submarine is 7 meters from the surface. The piecewise definition gave us a clear, two-step path: check the sign, then apply the matching instruction. You can use this exact same method to find the absolute value of any number, from your bank balance to a temperature reading. You already know the absolute value graph is a V-shape with its vertex at the origin. Now we're going to move that V around the plane. When you see an expression like x, 2, the whole V slides 2 units to the right. When you see x plus 3, the V lifts 3 units up. The sharp point of the V, which we call the vertex, simply moves to the new coordinates given by the numbers inside and outside the absolute value bars. Imagine you're standing at a point on a straight road and you want to know your distance to a specific landmark, like a tree that isn't at the 0 mark. The expression x gives exactly that distance for any position x. The graph of this distance is a V whose vertex sits right at the landmark. So by shifting the V, we can model distance from any starting point. In calculus problems, you'll often need to find the minimum value of an expression involving absolute values, and that minimum is simply the y-coordinate of the vertex. Being able to read the vertex directly from the equation saves you from having to plot points every time. Let's build this from the parent graph y equals x, which you already know. When we replace x with x minus a inside the absolute value, the graph shifts horizontally. But here's the trick: it shifts to the right when a is positive, which feels opposite to what you might expect. Think of it as the graph chasing the value that makes the inside 0. The expression x, 3 becomes 0 when x equals 3, so the vertex moves to x equals 3. Now, adding a number b on the outside simply lifts the whole graph up by b. If b is negative, it drops down. So the general form y equals x, a plus b has its vertex exactly at the point a, b. The horizontal shift comes from setting the inside to 0, and the vertical shift is just the number added outside. Let's solve a concrete problem. Suppose a delivery truck drives along a straight road, and a shop is located at position x equals 4. The distance from the truck to the shop at any point x is given by the absolute value expression x, 4. The graph is a V with its vertex at x equals 4, where the distance is 0. Now, the shop adds a flat $2 delivery fee regardless of distance. The new cost function becomes x, for plus 2. This shifts the entire V up by 2 units. The vertex moves to 4, 2, meaning the minimum possible cost is $2, which occurs exactly when the truck is at the shop. The horizontal shift tells you where the minimum happens, and the vertical shift tells you what that minimum value is. So the whole idea is, the numbers inside and outside the absolute value simply move the vertex, giving you the location and value of the minimum at a glance. We already know the absolute value of x, written as x, gives the distance of x from 0, making a V-shaped graph with its vertex at the origin. Now we ask a new question: how steep is this V at any point? The steepness, or slope, tells us how fast the distance is changing as x moves. In calculus, we call this slope the derivative. For a straight line, the derivative is just its constant slope. But our V-shape is made of two different straight lines meeting at a corner. So to find the derivative of the modulus function, we need to look at the slope on each side of 0 separately. Why do we care if a graph has a sharp corner? Imagine you are watching a ball bounce straight down onto a hard floor. Its distance from the floor decreases, then instantly changes direction and increases. The graph of distance over time has a V-shape, just like our modulus function. At the exact moment of the bounce, the ball's speed is not a single number, it changes from downward to upward instantly. In physics, this means the velocity is undefined at that instant. In engineering, sharp corners in a shape can concentrate stress, making materials crack. Finding where a derivative does not exist helps us spot these critical moments and weak points. So the derivative of the modulus function is our first simple example of a non-differentiable point, a place where the slope cannot be pinned down to one value. Let's derive this step by step. Remember the piecewise definition: for x greater than 0, x is just x. The graph is a straight line through the origin with a slope of +1. For x less than 0, x equals negative x. That graph is also a straight line, but it slopes downward, so its slope is -1. Now, what about exactly at x equals 0? The derivative is the limit of the slope as we zoom in. If we approach 0 from the right, the slope is always +1. If we approach from the left, the slope is always -1. Since these two one-sided slopes do not agree, there is no single tangent line that touches the graph smoothly at the corner. The limit does not exist, so the derivative at 0 is undefined. We call this a non-differentiable point. Let's solve a concrete problem. Imagine a toy car moving along a straight track. Its distance from a marker at time t seconds is given by the absolute value expression, distance equals t minus 2 meters. This is just our V-shape shifted 2 seconds to the right. What is the car's speed at t equals 1 second? At t equals 1, the value inside the absolute bars is 1 minus 2, which is -1. So the distance is the absolute value of -1, which is 1 meter. On this left side of the vertex, the graph is a line with slope -1. So the speed is -1 meter per second, meaning it moves toward the marker. What about at t equals 3 seconds? Now t minus 2 is +1, so distance is 1 meter again. But on this right side, the slope is +1. The speed is +1 meter per second, moving away. Imagine you have a smooth curve, like a parabola, and you wrap it in absolute value bars. That's a composite modulus function, something like the absolute value of f of x. Graphically, any part of the curve that dips below the x-axis gets flipped up like a mirror reflection. Now, we already know the derivative of a plain absolute value of x is a step, -1 for negative x, +1 for positive x, and undefined at 0. For a composite function, the derivative is almost the same idea, but we have to multiply by the derivative of the inside function. The result is f prime of x times the sine of f of x. The sine function just tells us whether the inside is positive or negative, giving +1 or -1. It's the chain rule, but the outer function is the absolute value, whose derivative is that sine step. Why do we care about the derivative of something wrapped in absolute value? Because the real world is full of quantities that can't be negative. Think of the distance between two objects. If a car is supposed to stay exactly 4 meters from a wall, the error is the absolute difference between its actual distance and 4. That error is always a positive number. If we want to minimize that error using calculus, we need the derivative. Another example, in finance, you might model a penalty that only applies when a value falls below a threshold. The penalty function might be the absolute value of the shortfall. To find the worst case or best case scenario, you need to know how that penalty changes, which means differentiating a composite modulus function. It's the mathematical tool for any situation where only the size of a deviation matters, not its direction. Let's build this from the chain rule we already know. The chain rule says, if you have a function inside another, the derivative is the derivative of the outer function, evaluated at the inner function, times the derivative of the inner function. Here, the outer function is absolute value of something, let's call it u. We already know the derivative of absolute value of u with respect to u is the sine of u. It's +1 when u is positive, -1 when u is negative, and undefined at 0. So, by the chain rule, the derivative of absolute value of f of x is just the derivative of the inner function, f prime of x, multiplied by the sine of f of x. That's the formula. But watch out, wherever the inside function f of x equals 0, the absolute value function has a sharp corner, just like the v-shape at the origin. Let's solve a concrete problem. A toy car moves along a track. Its distance from a wall in meters after t seconds is given by p of t equals t squared minus 6t plus 5. The safe distance is exactly 4 meters. The error, how far it is from the safe spot, is e of t equals the absolute value of p of t minus 4. We want to know how fast that error is changing at t equals 1 second. First, simplify the inside, f of t equals p of t minus 4, which is t squared minus 6t plus 1. At t equals 1, f of 1 is 1 minus 6 plus 1, which is negative 4. The derivative of the inside, f prime of t, is 2t minus 6. At t equals 1, that's 2 minus 6, which is negative 4. The sine of f of t at t equals 1 is the sine of negative 4, which is negative 1. Imagine the graph of the absolute value function, that familiar v-shape with its vertex at the origin. When we integrate it, we are asking for the area trapped between that v and the x-axis. But here is the catch, the v is made of two straight lines with different slopes, one negative and one positive. So we cannot just apply one rule across the whole thing. Instead, we break the area at the vertex, the point where the inside expression changes sign. We split the integral into two separate pieces, one for the left arm and one for the right arm, and then add their areas together. That is the core idea. Integrating the modulus means splitting at the sign change. Why do we even care about the area under a v-shape? Because in calculus, an integral often represents a total accumulated quantity, like total distance traveled. Speed is always non-negative, just like the absolute value makes things non-negative. If you walk away from your house and then back toward it, your velocity changes sign, but the distance you cover keeps adding up. The modulus function captures exactly that. It flips negative parts up to positive, so the area under its graph gives you the total distance, not the net change. So integrating the modulus answers questions like how much ground did I cover in total, regardless of direction. That is why we need a method to handle it. Here is the step-by-step method. First, find the point where the expression inside the modulus equals 0. That is the vertex of the v, where the sign changes. For a simple x, that point is x equals 0. For something like x minus 2, it is x equals 2. Second, split the definite integral right at that point. You now have two integrals, one from the left limit to the vertex, and one from the vertex to the right limit. Third, in each region, replace the modulus with its piecewise definition. On the left, where x is negative, x becomes negative x. On the right, where x is positive, x is just x. Finally, integrate each piece normally and add the results. The total area is the sum of the two areas. It is like finding the area of two triangles and adding them up. Let us solve a concrete problem. A toy car moves along a straight track. Its velocity in meters per second is given by v of t equals t minus 2, from t equals 0 to t equals 4 seconds. Notice the velocity is negative for the first 2 seconds, meaning the car is moving backward. We want the total distance traveled, not the displacement. So we integrate the absolute value of the velocity. The expression inside the modulus, t minus 2, is 0 at t equals 2. That is our split point. From 0 to 2, t minus 2 is negative, so its absolute value is negative of t minus 2, which is 2 minus t. From 2 to 4, t minus 2 is positive, so the absolute value is just t minus 2. Now integrate. The first integral, from 0 to 2 of 2 minus t dt, gives the area of a triangle with base 2 and height 2, which is 2. We've learned that the absolute value strips away the sign and gives us the size of a number. Now let's see 3 powerful ways this idea is used in the real world. First, if you have a velocity time graph, the area under the absolute value of velocity, ignoring whether you're moving forward or backward, gives you the total distance traveled, not just the displacement. Second, when a scientist measures something, the error margin is simply the absolute difference between the measured value and the true value. Third, when fitting a line to messy data, instead of squaring the errors, you can just take the absolute value of each error and add them up. This is called least absolute deviations, and it's a robust way to find a trend. All 3 are just the modulus function doing its job, measuring size, ignoring direction. Why do we need these applications? Imagine a car that drives forward 10 meters, then reverses 5 meters. Its displacement is only 5 meters from the start, but the odometer shows 15 meters of total travel. The absolute value is what the odometer uses, it counts every meter, regardless of direction. In science, no measurement is perfect. Knowing the absolute error tells you how much you can trust a result. And in data analysis, a single wild outlier can ruin a line fit by squared errors, because squaring makes a big error huge. The least absolute deviations method just looks at the size of each mistake, so one crazy point doesn't dominate. It's a fairer, more stubborn way to find the central trend in noisy data. Let's see how each one works, building on the integration technique we already know. For total distance, you find where the velocity crosses 0, those are the points where motion changes direction. You split the integral at those routes, take the absolute value of the velocity on each piece, and add up the areas. That's exactly the splitting the integral method we learned. For error margins, it's even simpler. You subtract the true value from your measurement and take the absolute value. If a standard weight is 100 grams and your scale reads 103, the error is the absolute value of 103 minus 100, which is 3 grams. For least absolute deviations, imagine you have data points and a candidate line. The residual for each point is the vertical distance from the point to the line. You take the absolute value of every residual and sum them. The best line is the one that makes this sum as small as possible. Let's solve a concrete problem. A car's velocity over 5 seconds is given by v of t equals 2t minus 4 meters per second. It starts moving backward, then forward. To find the total distance the odometer would show, we first find where the velocity is 0. Set 2t minus 4 equal to 0, and we get t equals 2 seconds. That's our split point. From t equals 0 to 2, the velocity is negative, so the absolute value is negative of 2t minus 4, which is 4 minus 2t. Integrate that from 0 to 2, the area is 4 meters. From t equals 2 to 5, the velocity is positive, so the absolute value is just 2t minus 4. Integrate that from 2 to 5, the area is 9 meters. Add them up, 4 plus 9 equals 13 meters. That's the total distance traveled. Notice the displacement would be different, it would be only 5 meters, but the odometer reads 13.